Okay, so what are those parameters? And these parameters, those parameters here, this is what I'm going to explain right now. Okay, once I switch back to the blank, and then come back from blank window, I come back to connect those items here with the ones I'm going to explain. So, did you start transformers with Professor Lazar? Guys?
not yet يعني لسه على أول شيء تقريبا لسه ما بدأ.
Okay, no problem. Okay, now a transformer. Let me just adjust my desk here. A transformer, it has like a core. We have two windings, and those windings, they are we wire those windings around the core itself. Okay, try to make it 3-dimension, almost something like this. تقريبا, okay. So accept my drawing. Now we have the primary. The primary we come. This is those are a plate of lamination plates, and all of them, they are connected together. Okay, like maybe we can have more than 30 plates. Sorry.
Sorry.
Yeah, we have more than 30 plates pressed together to make this transformer. I mean by this, look, you can go through any YouTube how this is built. I'm trying to be more. This is one plate, for example, and the other one behind, and so on. We have more plates here, and they are pressed together with the isolation. There's like a liquid to make isolation between them. That's why I don't know if you had the chance before, once you are a child or now in your life, if you go through next to a transformer, and I saw that back in the country there, you can hear a sound. That sound means it's old transformer, and the lamination, there is like a gap between lamination, and they vibrate between themselves, and they make that sound. This transformer should be changed. Okay, and this, if we keep this one for a long time, this vibration, the isolation between laminations will be between those plates will be gone, and it will create short circuit inside this transformer. You can Google it, and you can see exactly how it's constructed, this transformer, a single phase transformer, and it will give you more clear a view or idea about transformer itself. Now, once it's built, we come with a wire, and we start wiring this, make a spiral around this transformer like this. Okay, and doing this, we have what we call primary, and secondary will be same thing, the other side. Spiral here. Okay, we make it around like that, and we get two terminals. Okay, A and B. A and B here, for example, and that's the secondary one. Now, this is a physical representation for the transformer. Electrical representation will be like the first winding, the primary, the secondary winding here, and the core, the blue one, will be represented by two parallel lines inside. Okay, so this means we have a primary, secondary, and they are wired. They are wired around this core here, which is this those two parallel lines. Okay, yeah, so this is a primary and this is secondary. Now, how the secondary voltage is generated here, and also how we can reduce that the voltage from the primary to the secondary one. Let's say, for example, we have 120 volts connected to this primary. This is a supply, and supply here will generate a current. This current will go through this wire, this winding. Okay, and this the current will generate a field, a magnetic field inside this winding here. And this magnetic field will be circulated through that core. It's what you call core. This is a CORE. So the core. So this magnetic field will be circulating here. And this one, the phenomena will be reversed. Current generates field, voltage generates current generates field. Here will be a field, will generate, will induce a voltage E, induced one, IND. So induced voltage across this voltage, those terminals. If we need to have a current, we have just to connect a resistor or any load, and the current will start circulating. We need to close this loop here. The current will be generated from this source, from that source here. Now, the number of the wires, the turns here, and the number of turns of this number of turns for this primary and secondary will determine what you call the ratio for the transformer ratio. And usually what we do, we can call this one, like for example, 10 ratio 10 to 1. Doesn't it? Okay. So 10 to 1 means what? Means 10 volts given here at the primary will generate 1 volt at the secondary. 100 volts give us 10 volts, and so on. Okay, so that ratio, this is specific for each transformer, and this ratio it depends on the number of windings or turns. Sorry, for each winding from the primary side and secondary side. Okay, so that's the case for this transformer. Now, from physical one to electrical representation, we go to what we call equivalent of this single-phase transformer. Okay. Why we need this one? Because we need to do, if we need to do simulation or to do the study for your transformer, you have to make model for this one, and the model it's called equivalent circuit. So how we can model this one? We have different steps. I think Professor Lazar, even in the literature, they're going step by step. I've given you the last simplified one, which is here we have a resistor and inductor, which represents, this is R1 and X1, which X1, which represents the first winding, this winding here for the primary. So every wire has its own resistor, and once you make it spiral, it will create inductance. So that's why we represent that first wire here or winding with R1 and X1. Okay, the secondary here will be having its inductor and resistor, and we call it R2 and X2. Okay, now the core itself has, and those impedances for for primary and secondary, they are in series. R and C, R and X, or R and L, they are in series, represented like this, connected in series. For the core itself, this core, because the transfer of that this magnetic field through that core will generate losses. We have some losses here, okay, inside this that core. And the representation for that core, it's like another resistor and inductor, but in parallel, usually like this. That's the transformer. This is equivalent circuit for the transformer. Now, to connect this one here, to connect a secondary to the primary, we have to take care about this ratio. You cannot just take it directly like this, but and keep it R1, R2, and X2, but should be taken through that ratio here. So that's why we'll call this one, change the color, call this one X2 prime and R2 prime. Okay, and we connect this like that. So now this Z2 or secondary one prime represents the secondary transferred to or seen from the primary side. And here would be R naught, X naught. Okay, keep in mind for the core, depends on the literature, they call it R naught, which is equivalent to R core, equivalent also to R magnetization for the magnetic material. Same thing, this is R naught here. Same thing for X naught or XC or XM. Same thing. Okay, so here we have the supply, one, and here the secondary A2, that's prime. Okay. Dr. Lazar will explain this in details. Okay, in the lab, usually we give a brief explanation just to have time for the experiment. So that's the equivalent circuit. Okay, for your transformer, single phase transformer. Even if you have three-phase transformer, which are, I'll switch to another part, another blank window. The session is recorded and it will be posted for you. Three-phase transformer, electrical representation is like this. If it's connected in Y connection like that. So A, B, and C, or L1, L2, L3 from Kahroma, for example. And all of them, they are wired through that core, the magnetic core. And the secondary, this is a primary, and secondary will be same thing. Either can be in Y or delta connection, or delta connection, like this. And it will be A, B, and C. Okay, so this is a representation for three-phase transformer. This is small L1, small L2, and small L3. The equivalent circuit, since those ones they have the same number of turns, they are using the same wire, same material, so they should be equal. Okay, this part with this one equal. That's why the equivalent circuit will be same as the secondary. We represent only one winding, and this one winding will represent the three of them for the primary side. The same thing from the secondary side will be same, and the core will be same also. Okay, like that. Sorry for this drawing like that. But now the values for R primary side, for Z primary side and Z primary secondary side, of course, it will be different than the single phase transformer. And even their calculations their calculations will be different from single-phase transformer. But the equivalent circuit is similar, same thing in terms of representation. Now, going back to, if you don't have any question, I'll go back to my file to end my session. Okay, so here, if you remember, we have, let's switch the color to this color. We have R, L, R, and L. Sorry, I'll just erase this because they are not using that. They are using the simplification before the previous one I have done. Sorry. So we have a primary R, L, have the core R and L. Okay, and you have our transformer. This is before the last simplification. You have R and L, like this. So this one will be R2 now, not R2 prime. R2 prime will eliminate this this section here, and we will end up with our last simplified equivalent circuit. And this is X2, this is R1, X1, R, here they call it RC, and we have XM, you have R1, X1, and 2X2. Okay, so this is your equivalent circuit for that this exercise. Okay. Now each transformer, the one I showed you with the 3-dimension physical transformer, it has nameplates. Call this one. I'm typing my. We call this one name plate. So this nameplate, this nameplate has all information about each transformer in terms of power, primary and secondary voltage, the current, nominal currents, okay, I primary, I secondary, and the weight, the size, the dimension of that transformer. So we have a lot, and the manufacturer name, the part number of that transformer. So this plate, it's a metallic plate. You will find it on each transformer. Okay, especially the industrial one. So that one has those information. These ones here are part of this nameplate. So our apparent power for that transformer, the one we are simulating now, has 10 kVA. The primary voltage that can be supplied here is 200, sorry, or 2200 volts. And keep in mind, most of the time, as a standard, they are represented in RMS value, not peak value. And this one, if you use the voltmeter will show you in RMS value. For any, if you connect this voltmeter at 2 terminals. So this is a V secondary, 220 here as voltage. So the ratio here is 10. Okay, so 10 volts will give me 1 volt. Of course, 2200 volts, if you divide this by 10, will give me 220 volts at the secondary side. So this is what you call a ratio for the transformer. And it shows you exactly what is the maximum that you can supply at the primary. If you don't need to burn your transformer, you should not see that value here, okay, at the primary side. This transformer will work at 50 hertz. Okay, so those are the information that we need for our simulation. Okay. Okay, now I'll come back again to this window. I'll go back to MATLAB. So I'll share application with you. I think I'm already sharing the application with you. I'll start this. Do you see my Simulink file?
No.
No, okay. So this is the previous file. So from your side, you can open from here new model. Okay, or for my case, I'll delete this one, this model here. Sorry. Okay, and start my new model, another project. Okay, you can rename it if you like. Now, what do we need? We need a transformer, first of all. Let's minimize this one here. So open the library. From the library, just type a linear transformer. The transformer, this one here. Okay. Now, double click on it to change its parameters. Keep in mind, please, in your lab reports, I need to see for each block the parameter, and you can name it. You can give it a title, figure 1, for example, transform parameters. I need to see what you have done here inside for each block. Okay, if you remember in that lab manual, if you have it in front of you, we have we're given the whole parameters in per unit. It's written between parentheses per unit. So means the whole numbers we have there, we keep them as they are, and we enter them in those fields. If you do like next labs, once we do this open and short circuit tests, because we need to take our transformer and represent that physical transformer to its equivalent circuit. So we'll do some tests on it, open short circuit test, and everything will be given in SI. What we mean by SI means inductance will be not in per unit, will be in Henry. The resistor will be in ohm. So in your simulation for the other lab, the one with I think the third lab, once you do your simulation, you have to switch from per unit to SI and enter your calculated value here to simulate your file, your circuit. For this exercise, I'll keep it per unit. Here we have different fields. Sorry, the first field we're asking to enter. It's written here PN, nominal power, but they mean nominal apparent power, which is S, and it's seen here by this unit VA. If it's active power, it will be written watt here, but the root VA means nominal active power. Sorry, nominal apparent power. Active, which is P, reactive Q, and apparent power S. Okay, so we need the apparent power for our transformer was what? 10 kVA. Okay, so it's 10 e to the power of 3. That's 10 kVA. 10 to the power of 3 VA. The frequency in hertz. If it's written reading per second, I have to calculate, switch it from hertz to reading per second. So this one will be 50 hertz instead of 60. The first winding, the second field, first winding, we need the nominal value of the applied voltage that can be supported by this window, which is 2200, which is 2200 volts. The RMS. Okay, R1 should be the one you have in your lab reports. in the lab manual, sorry. I can't remember the value, but I'll keep it as it is right now. So here, R1, L1 should be the ones given in your lab manual. You put them here. Okay, winding number 2 will be same thing. So here will be 220 as secondary voltage nominal value. R2, L2, the ones given in the lab manual. Here, by default, it comes with the 3 windings, 1 primary and 2 secondaries. We need only 1 secondary. That's why we'll eliminate this one here, the third one, and take this. If I click on apply, it will become here only 1 primary, 1 secondary, and this field will be inactive. So no need to change this field here, the parameters inside. The magnetization resistor or resistance and inductance, the ones you have in your lab manual, you change them here. Okay, you put those numbers here. I think 100, and I can't remember the other one. I think here for R would be 100. The other one, I'll keep it now 500, but you have to change them. Okay, apply. Okay, now my transformer is set as required. Okay, the parameters given in the lab manual. Now, to simulate this one, we need to supply, okay, this primary by AC source. So I think if I write AC power, AC voltage maybe, yeah. So in AC voltage, we have this one. Keep in mind, please, you should not mix between the blue icons and the black icons. The blue one, if I take it with the black one, it will not be connected. You see, it's forbidden. It's not allowed. But what we can do, if sometimes you have a big project and one of the blocks doesn't exist in this library, I can use another library, but I have to use a block, call it physical, converter with physical to Simulink, for example. Simulink to physical. So we can do that, but for our case, we don't need it. We'll select black with black, and that's it. So I take this one as a source. So here it can be now connected. I can resize transformer, the source as I need, or I like, okay, just to make it a little bit bigger. Okay, so this is now my transformer and supplied with the AC source. If you go back to the file and come back to my file here, simulation file. Okay, this is done. This is the first step. Parameters for the transformer, they are set. You have just to enter those values in the field, the right fields. Here now, once it's built, we need to record 3 parameters for each test: the open test and short circuit test. Now, where we use this open and short circuit test, we use them in low level side, which is the secondary. Low level means secondary winding, and high level means the primary winding. Now, where we have to take those measurements in the high level, high voltage side. So there we have to take volts and current and the power. Okay, so voltmeter and ammeter and wattmeter should be connected in the primary side, not secondary side. Secondary side, we keep it, either we keep it open or we make short circuit on it. Okay, now I'll go back to share this with you again. Okay, so this is the file. Just make open this behind just to make it more clear. White background. So I told you we need to measure the voltmeter across the primary. So we add voltmeter here. And we need to measure the current going through this primary. We add a meter here. And we add the block to calculate the power in the primary side. So going back to the library, we need the voltmeter, we call all of the measurements. Just keep in mind, you have to spell it well, and it will give you the right blocks. So measurements, we have a lot of type of measurements here, pressure, temperature, and everything here. So we look for one which is called, I think I skipped it. We have voltage measurement. I need this one. I need the current measurement here. Okay, I need the power measurement. Yeah, power here. Okay. So now I can display them through oscilloscope, or I can use a display to display number. So that's why I look here for display. I'll write display. I have one display here, and after that I can copy and paste it many times. Now to display a value, keep in mind this voltmeter or voltage measurement and current measurement, they measure during time, so they measure a signal. Okay, if you connect this one directly to your display, okay, anything measured here as voltage will be swinging here, will be going positive, negative, positive, negative. And once the time of the simulation time stops, it depends. Maybe it will stop in negative sequence, one point at the negative sequence or positive sequence. So it will show you that last point. And this is not the case. No, we don't need that. We need to collect the data from that signal and calculate RMS value for that one, and display only one value here, which is the RMS value. That's why I go back here and write RMS. RMS. That's not RMS. There's RMS, but with the blue one. That's blue text. That's the one which is working fine with this library here. Okay, sync. It should be somewhere here. Something similar to this one, but not that one. Okay, for the time being, I'm going to take this, even if it's not working, but I'll search for the other one. It looks like this, but RMS written here in blue. That one works fine. Anyways, I skip that part. So let's close or delete that one. This is a voltmeter. I'll print that one here. And to have a positive to the positive connection. Yeah.
If you double click in the blank and write RMS, you will find it.
This one here?
No, the blank page. No, not here. double click on yes here. Double click. No, not in this window. In the other window.
Here.
No, outside this window. In the
Yeah, here.
circle.
Yeah, here.
Yes. Double click. Yes.
Oh.
No. It showed you a search. If you double click.
Yeah, 1 second. And if you need it, I'll find it. Okay. Okay. Next. No, this will take us. No.
A double right click. Left click here and I found it.
Yeah.
Yeah.
It depends on the version. Okay.
Okay. I found the blue
just,
RMS.
Yeah, it's okay. I will find. I need just to continue this recording perfectly, and after that I'll search for that. No problem. And it's just to show how we can connect the components. So this is a voltmeter. Keep in mind it has a positive connection or terminal and negative terminal. Okay, so this one to the positive, this one to the negative terminal for your source, and a meter will be should be in here. So I'll delete this wire and insert this in between. So that one also has positive. So we enter by the current from this positive terminal and come out from this negative terminal here. Okay, so this is the current. Okay, now we have another terminal. If you see it, it's called I and V. Those for the measurement. So you can call signals from these parts. Okay, and display them in oscilloscope. So we need oscilloscope here. Right, scope. Take this scope here. I think we can collect collect signals and put them in one screen. So I write max here. This max one. So I'll collect the first one here. So it's depends on the sequence here. If you collect volt, so the first signal will be volt, and the second one will be current. Okay. Now the power here, we need of course to take the RMS for each one of them and calculate it before we go to that power. Right click. Drag, connect this one here for the volt. This is VI. So this V will be connected to the voltmeter and I to current. Let's say that's the current here. Okay, the display here will be going to a display like this. And also, I can display the value of the voltage and the value of the current in terms of RMS at the primary side. The secondary will be kept open for the first test and just adjust values here. This one, it's okay. It requires a peak value, and we will give an RMS value. So convert from peak to from RMS to peak. We take square root of 2 multiply by the value in RMS value, like this. So this is a peak value. If it requires RMS, keep it only 2,200. There's no phase shift. The frequency will be, it's written in hertz. So I type this one, 50 hertz. There's no sampling, nothing. So we keep it like this. Okay. For RMS values here, run RMS. Okay, I'll keep it like that, and I'll come back to the previous one. I did the one, the right one, and show you what is as what results can we get from the right one. Now it's done. The transformer we set is its parameters. Here the source already set. We need it's 50 hertz, so 0.2 will give us like 10 sequences. I'll reduce this one to 0.1 to have only 5 sequences, and then run my circuit. If there is any error during the compilation, it will be shown in the MATLAB script. Otherwise, it will pass and go to simulation part time. Yeah, the error here, I think doesn't accept this one here. Okay, one port, this one here. Okay, let's delete this and search for the right one. Go to source sync. Sorry for this technical or sound, let's call it sound interruption. I need to complete that circuit before we start. The one who found this, what is the name of that block, please? RMS?
Yes, it is RMS.
Only like this.
It's I can share.
No, that's fine, that's fine.
It's called RMS Electrical slash Specialized Power System. Under
Maybe under this SIM cap. No. Okay, you'll find it. You can find it, but I'll take it from. I'll open my previous exercise. Machines. This one. Nothing. Good. I did save it.
Doctor.
Yeah.
I find the way. Go to the library browser again. Yes.
It depends which toolbox.
Up in the search, on the right, you see this. This is scope. Yes. No.
Which one?
Up in the search bar. Yes. On the right. On the right. Yes.
No.
Yes. Yes.
That's my right.
Click it and choose match whole word.
Choose what? Sorry.
In the search bar, on the right side of the search bar, you see this scope. Not yes, yes. Click it. Not this, not this. The the left. Yes, this one.
Yeah, it shows that thing.
Click the arrow, the black arrow. Yes, match whole word. The last one. Then go to the search and click enter.
Yeah, this is the one. This one. Thank you. Okay. So as you can see here in that display here, it displays a value, but it's not exactly what is the value here, RMS value. 2,200, but here it's more, 2289. Why? Because those blocks, we have to adjust the same frequency as the circuit itself. So instead of 60, we'll make it 50 hertz. Same thing for this one here, 50 hertz. Now if I run again, yeah, so it's 2,200. Okay, across that's primary here. So the current circulating here in the open circuit is very small, 0. Which is 4.6 milliamp, which is correct. So that's the power. Also, I think here we have to, yeah, we have to adjust the frequency also. Run it again. So that's the value. Okay, if you multiply this by this, but it depends on also on the phase shift. Okay. Let me do one thing. I can also do this. It shows here 0 power. That's correct. You know why? Because it's open circuit. There's no power required from the secondary parts. Okay. Now, in your lab reports, the first column for your first for the table, you requested to record those three numbers at the open circuit. So you have 2,200 and 4.6 milliamp. Sorry, 46 milliamp and 0 watt. If I do short circuit and run again, the values will change, of course. The current will be higher a little bit. The power here is the same, and the voltage is same. Okay, I think this one has a problem. If you click, if I make like 5, or maybe I have to remove this one here from the way. Yeah, this should not be there. Yeah, so this is the value for short circuit test. And this is right. This current is okay. 28.4 amp. Okay, and we see it in practical part in one of the experiments. If we need to do short circuit, either for a transformer or for the machine, rotation machines, we have to take care about in short circuit. So short circuit, in physical short circuit, which is a wire between two terminals for the transformer, and by holding the rotor for the machine, by holding it and making it our block it, holding it by hand, or holding by we have a system to block that rotor to rotate. This is short circuit for the machine. We should take care about the supply, the voltage at the primary. We should not exceed the current at the secondary, the nominal one in the short circuit test. So we'll see that one once we do the experiment, inshallah. So that's for this experiment or this simulation or lab number 1. We need you to be familiar with the Simulink, from where you can get components and blocks and how we can change their settings, how we can collect their signals. I forgot to open that oscilloscope and check the signals in there. Okay, so we have the primary and the voltage and the secondary and the primary currents. Look, if we need to display both of them in the same window, the scale should be taken in consideration. For that case, I have to enter in this place here, like a gain to make it or rescale that signal. Take this gain here. So you make it. Of course, I have to do it. Sorry, not here, but Control Z. If I put it here, the current, the power will be bigger, will be changed. It should be here before the signal, before display the signal. So I multiply this by 10,000, for example. The signal coming here will be amplified a little bit. And I think, yeah, still in 1,000. It's not enough. The 100,000. Okay, let's remove this short circuit here because it's amplifying the current bigger than the voltage. Yeah, like this. Okay, so the value shown here should be divided by 1,000. Okay, if you need to measure here. Now, how to measure? Using cursors in your screen here. There's this icon. If you drop that list and open this element here, so the window will appear. I think I have to click again. Yeah. So now I have the cursors. Here, the first voltage one is selected, the yellow one. So you can surf with this one here. You can scroll left or right. If I keep this dot here on the top of this signal, it will show me here the maximum of that signal, which is 2,200 right by 1.41 or 1.14, which is the square root of 2. So that's the maximum. If you need to measure the maximum of that blue one, you have to change it to its written gain, because that's the gain connected to the oscilloscope. And there you can move this little bit here on the top. This will show you, which is 65 milliamp as current. Okay. Of course, there is a phase shift in between, and that phase shift also can be measured. Okay, as we did, if you did with me, you took with me electric circuit 2. So you can bring those two cursors here, approximately something like this. So when the signal cross 0, and then you take this delta t, that value microsecond for I think 944 microseconds multiplied by 2 pi and multiplied by 50 hertz will give you delta in degree, the phase shift between the voltage and current for that transformer. Why we have this shift? Because the winding for the primary is its impedance. So the impedance, it has imaginary parts. That imaginary part creates a phase shift between the current and the voltage. And the current is lagging the voltage because the winding are represented by inductance, not capacitor. If it's capacitor, this will be leading. The current will be leading the voltage. So this is a small explanation that you can, for example, add in your discussion in your report. I think I went through everything this session. I tried to cover everything, and if you have any questions, you can still ask right now, or you can send them by email. Okay.
Doctor.
Yeah.
Why we don't use marxism?
Some of the components you will not find them like machines, DC machines, synchronous machines. You cannot find them in the multisim, but they exist in Simulink.
Okay, thank you.
You are welcome.